The next tool we'll look at in Minitab is regression analysis. And we're going to particularly look at the fitted line plot, general regression analysis, and I'll show you then this best subsets regression analysis. And what we're going to do is we are going to use a very simple data set at first called casting, just to be able to understand what does a simple fitted line plot tell us, and how do we get this graphical image out, which we were just talking about in the prior lesson. So if we go to Stat in Minitab, we see that the second curve is regression analysis. And what we're going to do is we're going to talk about the fitted line plot. Now the fitted line plot is a little bit limited in Minitab. You can only analyze two variables with respect to each other. And so as we take a look, the data set we have here is called casting. And this data set has a well, let me explain a little bit about what we're looking at. So a casting is where we take molten metal, heated metal, it's been liquefied, and we pour it into a mold, okay? And the idea is that mold then solidifies, then what's left is the metal is shaped into some sort of geometric shape that is useful for us. And at the same time, there's a little small piece that's called a test piece. And the test piece is used to test the breaking strength, which says, is this mold actually going to be, was it done right, okay? Does it have the right hardness? So, in order to test that, what we want to do is compare then the casting, its strength, to the test piece strength. And so the response is casting, and the predictor is test piece. So the question we're asking is, how well does the test piece reflect the strength of the casting itself? So when we test both of them, we can compare those. So that's what's been done here. Now, after we selected casting as the Y and test piece as the X, what I want you to do is get into the habit of choosing cubic as the relationship. Now, I don't expect that this should be a cubic relationship. My desire would be that it's a direct linear relationship, so that the test piece, indeed, its strength does reflect very strongly the relationship of the strength of the casting. Now, the reason I choose cubic, or request you choose cubic, is that it will actually analyze a linear relationship, a quadratic, or a cubic relationship. If I just choose linear, I'll never see the quadratic or cubic fits. And so if I see cubic, I can go back and then get a graph that's linear. So it's going to graph the cubic graph, that'll be the outcome we see. And then it will also tell us which is the best fit. And again, if I choose linear, it wouldn't do that. So we go to graphs, and this is about the residuals. So again, we're going to talk about residuals analysis later, so I'm not going to select that. We'll come back into that topic. When we talk about options here, I can do some transformations. However, I don't want you to do transformations. I want you to take a look at data. Remember, we're looking at dirty data and messy processes. And as a result, what we want to do is just look at the original data and the way it came. I could store data, okay? And if I store data, I could store the residuals, or I could store the fits. This will be also something that we will use when we come back to residuals analysis, so we'll skip over that. And so we just click OK. And what we get now are two things. We get a session window, and then we get output from the session window here. Okay, and so I'm just going to make that a little bit bigger. So we see all of that. And then we get the fitted line plot. So the fitted line plot is here. Okay. So these are the two outputs that we have in terms of the session. Now, we take a look here and we see here is this equation. So that's the regression equation. So that is this fitted line plot. Now, take a look at that. That looks actually pretty linear, doesn't it? So we take a look and say, okay, the source, here's a sequential analysis of variance down here. Okay. And as we take a look at that sequential analysis of variance, this is linear, quadratic, and cubic. So it says the variation actually as linear was statistically significant. So that says I don't go to the second or the third because I don't want more complexity in my equation than I need to have. Okay. This is explaining 43% of the variation in the R-squared adjusted. That's not much, but it is statistically significant. Now, when I say that's not much, what I mean is for a linear regression analysis, I would like to see better than a 70% R-squared adjusted value. Okay, so I take a look at this, And what's happening? Notice how I have this wide banding. You know, there's a very big difference around that line. This line, it's almost straight, okay? So let's go edit the last dialog box. And let's change this to linear, okay, instead of this cubic fit that we had. And so now I see here's a linear relationship, okay? Now, can I improve my understanding of this? Well, actually, I can. Let's go back to edit the last dialog box one more time, okay? And we see under this options, I could have displayed the confidence intervals and the prediction intervals. So what does that give us when we do this? Now notice the graph difference. Okay, so here's the graph with, whoops, I want to see the other graph. So here are the two linear graphs side by side. Notice the difference. So here I have these dashed lines here. This is called the confidence interval. That's the confidence that this regression equation is actually fitting the data. It says I'm 95% that my equation will fit data from this low spot to this high spot, or from this high spot to that low spot. In other words, it's pivoting around the mean. And notice how these lines are pinched in a little bit here, because that's basically a function of measurement error. Okay? Now the other lines we see, these are the prediction intervals. That's these lines out far. And so those dashed red lines are saying, let me blow this up so you can see it a little bit better. Those dashed lines are saying if I was to get another test piece at 80, the casting would be somewhere between, and that looks like it's about 58 and about 100 and maybe 3. Okay, so it says that's the expectation. If I have a casting at 60, I can see that it could be almost anywhere. That's why this R squared adjusted is 47, because it's a 50-50 shot where you put that. Okay, so that's saying the test piece is not actually a good predictor in terms of the strength of the casting. So, guess what? All castings and metal things use the test piece. That's a tradition in that industry. They test it to be saying, is the casting actually adequately strong? And so what we can see from this data is that's actually not a very good test. Why? Well, the test piece is a square block. The casting itself has angles. It's got geometry. It's like the housing of a transmission, or the rear axle, or it's the head of an engine, or it's the engine block. And that geometry itself has a lot to do with its strength. And so we take a look and say, if you compare just a chunk of metal in a rectangular, like a gold ingot, for instance, and you break that, that will indeed have two different items that are talking about strength. One is the geometry, and the other is the quality of the casting. And so quality of casting is not unique in this test. So again, this is something that we can start learning about and start seeing, is there a way to take a look at this type of estimate better? What we see now is regression analysis is a very powerful tool. And many people like to lead with regression analysis. However, we have to remember, it's best to understand all of the physical conditions of the process, the reasons for failure, and what's going on. If we don't do those things, which happen in the measure phase, we get to doing regression analysis too soon. We don't understand what's in the residuals. And understanding the residuals is going to be a key ingredient to successfully completing more complex types of projects. Because we'll understand many things, but we won't understand the things we don't see. And if we can't explain that variation, then we won't have been able to solve the solution forever on a particular problem. So understanding what's in the residuals is going to be the next focus area that we have to concentrate on.